Yeah, when we have some new idea, we think, here's some cool quantum information theory stuff. Then we go to Mark and we ask, hey, what do you think? What is it going to look like in your network? Makes sense. Yeah? Usually he comes up with some good answer, I have to say. I'm very much looking forward to your talk, Mark.
I'm representing the user community here, I would say, yeah, since I'm working for a telecommunication provider, and Matthäus, my colleague, is giving you some, yeah. And at the end of the day, telecommunication providers have to actually integrate and make use of all the technology that you presented and maybe the protocols, and have to come up with a service offering, yeah, towards our customers or business customers. Yeah, and this is in principle the topic of my talk today. So we're stepping a little bit in the future now. Yeah, so we are assuming that all you guys did your work. And we got the equipment, so quantum storage, quantum everything, and we can integrate it into a network to offer a service, yeah, for our customers. So in principle, that's state of mind, yeah, that I prepare for this talk. But first, the team, the people. So I would say 60% of the people that are on the picture are actually working for quantum technology at TLabs. TLab itself is the research arm of Deutsche Telekom. That means we are mostly collaborating with universities and startups to get innovative technology in our networks and see what's in for a telco provider. And quantum technology obviously is there pretty well suited. Yeah, we're mostly looking 5 years ahead. Yeah, we learned also that's maybe not the historic timescale for mature quantum technology, but nonetheless, yeah. So we have to get ready, and we have to prove in terms of quantum communication that our networks are ready. Yeah, and this is why we're here. Yeah, and I always hope that we find a cool use case. Yeah, that we can also sell internally. Yeah, to actually make investments possible. Yeah, and to speed up things, right? And so I mean, you see our Berlin location, and here on the lower right. So where's this? The laser is here. That's for example, our QKD installation. Yeah, so we started in 2019 setting up a QKD installation with the Open QKD project. When we say we set this up, this means we don't do anything of that what you're doing. Yeah, so we're starting at the black box level, I would say. Yeah, we got them from IDQ and from Toshiba, these devices, and we're integrating them into the network. So we do everything you don't do. Yeah, so yeah, we're caring about key management, about safe key storage, about integration to the encryptors. Yeah, we try to do it in a most secure way, because if you do a mistake there, obviously this entire infrastructure is corrupted or is possibly corrupted. Yeah, so it's actually the other part of the coin that you have to do, and you have to do properly. Yeah? And you want to do it in a way that scales and so on. So, topic of the talk. So Janis agreed to talk about the quantum internet, yeah, and how telcos see the story, yeah. I mean, you see the nice pictures. I mean, it's taking out of the internet. You see the main capitals of Europe, yeah, interconnected, and they're sharing entanglement, and that's in principle the enabler for the quantum internet. I think that picture really makes sense, yeah. And I personally believe that telcos play a vital role in there, yeah. So we will be the entity that will take care about creating, distributing, storing, and exposing entangled states, yeah, to make quantum communications available in the future. Yeah, and we're not building the technology, as I said in the starter, yeah, but we're actually caring about the integration and setting that up as a service offering for customers. Before you usually kick off with technology, I mean, you always ask, what is it good for? What can we use the quantum internet for? So, I mean, maybe we quickly go through the list of 10 items or so. Yeah, there's always quantum key distribution. Yeah, that's a well-known service. Yeah, so for secure networks, we had a couple of talks about that. I don't know. So what we have today with QKD, so the prepare, measure, and maybe also the entanglement QKD systems, I don't like so much, yeah, because of the trusted nodes. Yeah, I think for a large-scale service offering, that's a no-go. Yeah, would you, as a customer, maybe responsible for military services, something, or secret service, trust a telecom operator to do a job properly at the trusted node and pay millions of euros for that? I'm not sure. Yeah. That's why we need the quantum internet. Yeah. That's the big game changer, because you get rid of these trusted nodes. Yeah. There's fiber channel sensing. Yeah. From Sykat's talk, I mean, he had a nice use case on its slide. Where he could show the switch on, switch off, yeah, of a tapper, let's say, trying to get access of a channel. If you could make quantum technology or use quantum technology to make sure that your channel is not tapped, yeah, maybe we can use maybe post-quantum cryptography does the job, yeah, to actually create enough secure communication channels. I don't know. Superdense coding we have, yeah, that's a nice use case that is on the agenda of the QRN project, but only giving an advantage of, I think, 1.44 I saw, yeah, maximum of 2. So also not so challenging, I would say, not so super interesting, yeah, because the repetition rates are also not so high with quantum communication systems. But there's quantum teleportation, yeah, and that's actually the first biggie on the list, I would say. Yeah, this is the bread and butter use case for the quantum internet, especially when you look at quantum integration of quantum computers. Yeah, so the story behind that is you have 2 quantum computers of n qubits. Yeah, so you can compute in this number space of 2 to the n qubits. If they're fully integrated, yeah, you end up with 2 to the 2n qubits. Yeah, well, when they're not, it's 2 times 2 to the n. Yeah. So you're dramatically increasing your number space, yeah, when you integrate quantum computers. It's a good story, yeah, once you have the quantum computers and they are error corrected and everything. But I expect this to happen in a hall, yeah, in one place, yeah. So the lines will be a couple 100 meters and not the full-scale telco network, yeah. So to get this to telco networks, this might even take some time, yeah. But nonetheless. There's quantum time synchronization, yeah, where you use entangled photons to synchronize clocks. I mean, we heard about this also in another talk. I don't know. So when you look at the resolution and the jitter of the technical instruments, yeah, like detectors or time taggers, you end up with 10 picoseconds, 100 picoseconds. I don't know. We are better classically, yeah. I mean, you have to keep this in mind, yeah. So OTTL step, so optical time transfer, electronically stabilized, the best point-to-point optical technology goes beyond 1 picosecond already now, yeah. So in order to be interesting, I mean, we have to get better, yeah, with quantum time synchronization. Yeah, that's my opinion. Sensing, I mean, I don't have to say so much, yeah. So Caspar is actually showing his project. And all the details on quiet. Yeah, that's a quantum sensor that is using quantum technology to sense electromagnetic fields, but it's not spinning out a classical bit as answer, but a qubit. Yeah, and this qubit we want to transfer over the quantum internet into a central quantum computer or interferometer or something. Yeah, so you have to transfer quantum states. And you need a quantum internet for that. Yeah, at the end of the day, I think you would teleport them in the future when we have this available. There's analog computing on the physical layer. That's also not so bad, I would say. That use case, it's a latency story behind that. Yeah, so if we can actually do analog computing on the very lowest layer, we don't have to virtualize into VMs, into containers, into network slices. Yeah, this all takes time. Yeah, but on the other hand, we have to find a use case here where this is really beneficial. Yeah, to do this on these physical layer computations. There's tokens that are around, yeah, where you use entangled states that are stored in a storage device to use them as tokens. There are paths, yeah, we had this on the poster, I think, yeah, Nilesh, yeah, we showed that for authentication of the quantum and also the classical channel. It becomes important later when you look at the architecture. And I don't know, maybe that's actually the glorious vision, yeah, that I have as a telco person. I mean, maybe in 100 years, when we have a telco network being a quantum computer. You never know. Yeah, so that's in principle what keeps us working on that topic. Yeah? So how do we do it? That's now the topic of the talk. I have 2 slides with quantum technology. This is taken from the QRN project. Saikat actually showed it also yesterday in a different view. So there are two protocols available. There we have, one is the node sends photon protocol to build a quantum repeater. The other one is the node receives photon protocol. Yeah, and they have the pros and cons. So in this protocol, I mean, you have to look at the blue balls are also always the atoms. The gray balls are the photons. In this case, you have two atoms here and there. They're sending an entangled photon with the atom, yeah? And the photons are actually being conveyed into a Bell state measurement. And if they are projected in the Bell base, entanglement is swapped, and suddenly the two atoms are entangled. You do this on both sides. Later, you do another. No, this doesn't work. Another Bell state measurement in the middle, yeah, and you can actually then start swapping your entangled states through your network. That's what telcos, to my opinion, have to set up. Yeah, and this is actually the key mechanism to set up this quantum internet. Watch on, okay. Here we go. So that's the other one. There's slight differences. Yeah, so you have a photonic source in the middle that is sending now the entangled photons, and you have the atoms at the QR cell. They're also sending their photons entangled with the atoms. You do the Bell state measurement then at the quantum node, and it ends up the same way. You continue with swapping, and at the end of the day, you end up with something like that. Yeah, so you have a network with lots of nodes. You have pairwise stored entangled states in the network nodes. Yeah, that's the outcome of this step that I just showed. And this should happen at maximum rate. Here we learned that 1 gigabit is maybe possible. Yeah, in the future with quantum dots, and if they can be stored on the other side. The Bell state measurement takes you away, I think, 50% fidelity. Yeah, so you see with every swap later and with every BSM that has been conducted, I mean, you lose rate. Yeah, so we start with a gigahertz, but with every step in that process, the rate will actually diminish. So the next step we all know is swapping. Yeah, and off and on. Okay, you see pictures like that. Yeah, so here's a small network consisting out of 5 nodes, and you have shared entanglement between the neighboring nodes. Yeah, and then the interesting part is actually here at node C, because node C has more than one partner and more than 2 partners. Sorry. And no, it depends. Yeah, so node C has to swap the entanglement either from B to D or from B to E, and has to keep some entangled states to its own. Yeah, so that there are enough to ensure a final state that every node shares entangled states with every other node, because this is what we want to achieve. Yeah, and the logic of C, who knows that? Not the provider of the entanglement distribution system, right? I mean, I think that's telco knowledge. Yeah? And this is why I actually always advertise a view, a disaggregated view, yeah, that here we go. Yeah, the quantum technology. So the quantum system vendors in the future that building these storage devices and everything, they're running the actual entanglement distribution on the physical layer. They care about the. So I wanted to point to node C. Yeah. So the basic entanglement distribution between neighboring nodes, yeah, it's a process that has been executed by the system vendors of the quantum storage devices, yeah, on the physical layer. But the activity of node C, yeah, this is telco knowledge, and I think this should be done by a telco system, at least running the responsibility of a telco provider. And it's even better, yeah. So telcos usually know exactly in their networks what traffic, yeah, goes into the network and what traffic goes out of the network in every node. Yeah, this is normally mapped in these traffic matrices. Yeah, so where you note down this relation. Yeah, so we know exactly what's needed, and I think we will also know this in a future quantum network. Yeah, so we know the demands of of quantum communication protocols at the various nodes. Yeah, we know from history, we know from experience, and this is in principle your feed-forward system. Every day, yeah, because it changes every day. Yeah, on a bank holiday, it's different than on a normal weekday. On a weekend, it's different. It's different. It differs by time of day, even. Yeah, which demands are really required to fulfill the job. Yeah? And this is your feed-forward system, how you steer your entanglement distribution, your swapping mechanisms across your network. You also probably need feedback, yeah, which means are there any fluctuations to that feed-forward? Where I come to in a second. And this, the second part of the story is the resource management, yeah, of your network capabilities. I mean, the network provider already has this knowledge, yeah. So we know what links we have, how many links we have, what the attenuation of these links is, what the repetition of the photon of the lasers are to pump the quantum dots or the color centers. Yeah, this is all knowledge that can be steered by the provider, and it ends up with a big optimization problem, right? I mean, a classical optimization problem. What's the best way, yeah, to distribute the entanglement across the network and then execute or make the physical layer execute the swaps in the right order, yeah, in order to fulfill the traffic demands. And I think that's telco responsibility. So how could this work? So I brought this slide. It's a little bit more detailed, but you see again on the very top, so two quantum storage devices, yeah, that are now running the node send photon protocol. Yeah, so you have the atom again, you have the photon again. They're both entangled, and the photon has been sent out, and this is happening now. Assume that at a dedicated time slot. Yeah, so you have the time slot, and you have the partner, the quantum channel. And I now argue that when I even know the offset of the other side here, I can somehow align through a timing the two photons that are actually belonging to each other as an entanglement pair. The offset has to be trained, yeah, and it has to be feedback stabilized. We heard this in the first talk this morning. There's a task, yeah, but I assume this happens, and this would actually give me the chance to create an ID, yeah. And I can do this really locally, yeah, because I have the aligned time bin. I can create a local ID without a communication to the other node, yeah, and give that photon or that atom in my quantum storage that name. Yeah. I also know which atom it is. Yeah, I assume, let's say, a chip with 1,000 quantum dots on there, yeah, and I number them, yeah, 1 to 1,000, and I know exactly which atom has emitted the photon. Yeah, and these two identities I actually only export now in a classical mirror. That's the idea. Yeah, it's classical, yeah, because I want to keep this for householding, yeah, for housekeeping. And so think of a classical database where it's this unique ID that's the same on both sides, yeah, because it's been created from the partner, from the quantum channel ID, and the timing, yeah, that has to be realigned. And the partner ID is actually indicating the other node where this entangled state is shared with, and the storage ID is in principle the number of the quantum dots, so to say, on the chip. Yeah. So when I'm going to use that later for swapping, I can identify the atom, yeah, that is entangled, and I can make it do something. Right. That interface has to be implemented by the quantum system still. Yeah. Now the photons go to the BSM station. They do the BSM if successful, so if being projected in the belt state. The protocol layer will give the classical message to the mirror databases. And this is actually the indication. I put it here as a created ETS. Yeah? This is non-entangled state. Yeah? And I can reuse that when there's a created ETS. Yeah? So I know exactly when this happened. I can manage coherence times, yeah, so to see that it's still coherent, and my classical mirror is actually up to date. When I want to do swapping in that picture, it looks like that. Yeah, it's a simple protocol. You accelerate it in parallel all the time. Yeah, so the middle node, so B, is the one that got from the control system the command to swap. Yeah. This means the middle node is now identifying the newest entangled atom in node B with node A. Yeah? How do you do that? I mean, you ask your mirror. Yeah? The mirror has been asked, give me the newest entangled pair with node A yeah, and give me the ID and the storage. So the storage identifier, so the number of the quantum dot that is actually holding the atom. Yeah, does it the same way with node C, and then he's actually firing off, giving a command. Quantum storage, yeah, put these two atoms into a Bell state measurement, either by photon conversion or whatever meaning, I don't know. And the result of the Bell state measurement is then being broadcasted to the other nodes. Yeah, and what they have to do, they have to do housekeeping. Yeah, so this means the IDs, they have to change. They have to be updated. Yeah, there's a new ID. This could be the timestamp of the Bell state measurement plus some channel identifier. And the part ID has to be updated, the created as well. Yeah. So this is in principle, let's say, a classical view on how this could work. Yeah. It has to be fast enough. Yeah. So the first creations on gigahertz, it's challenging. The more Bell state measurements you do, I mean, it goes slower and slower and slower. You end up with megahertz, I think no problem. Yeah. And even with gigahertz, I mean, if you assume a server, a classical server, high performance, they have 3 to 4 gigahertz CPU speed, but 100 threads. I think that's possible. We get this. Yeah. And that's something we're working on at the time being, just to see if the performance is achievable. You know? So this is what we have. That's the final state. Yeah. So we have quantum storages, and every node, in every quantum storage carries entangled states. Yeah, with every other node, and they are there and are ready to be used, right? That's the future, the nice future. And I see this actually as telco responsibility. Yeah, you can build a service out of that. It's the entanglement distribution service. Yeah, and yeah, you end up with entangled states at the quantum storage devices, and you have to expose them now. Yeah, that's the next part of the story. If you look this in architecture, it looks like that. Yeah, pretty simple. Yeah, so. On the right side, there's the network provider plane doing what I just explained. Yeah, so we have a physical layer that is doing entanglement distribution and entanglement swapping. Yeah, that's implemented by quantum devices that we will not build, but we will in the future be eager to buy and to operate. Yeah. On top of that, there's a protocol layer out of classical systems, and they're running the protocols that I just explained. I mean, there are more when you look into usage, but there are classical protocols that are interacting with the quantum storage devices. And on top of that, you have an access layer because you want to actually have customers accessing your systems and asking for entangled resources, right? I mean, you have to somehow open that up for your applications. And on the other side, there's an application plane having the same layers starting from the bottom, again, a physical layer. Obviously, I mean, they want to digest quantum states, they want to send quantum states, maybe they want to swap out entanglement out of the provider infrastructure, what have you. To do so, they need a protocol layer to communicate that and align that with the provider infrastructure, and an application layer, I mean, to get the process started. Yeah, that's the idea. And here's a picture that we had before. I mean, it's a use case of quantum sensing. On the left side, you have the quantum sensors. Example, you have an acquired project, and you have an interferometer sitting at node D. We assume now that there's entanglement shared between quantum storages at A and D, and then there's a teleportation protocol executed to send or to teleport the quantum states, the classical signals, to D and reconstruct them and put them into interference or write to the quantum computer or what have you. Maybe I don't go too much into detail. Yeah, so I asked myself what interactions there are from user side, application side to network side. Yeah, so there's obviously quantum state out. Yeah, so it's an example to QKD protocol. Yeah, so you want to do QKD. That means you ask the infrastructure assign or identify two entangled photons. Yeah, at node A and B, and the infrastructure is actually creating reserving the individual pairs. They know the photon, the storage ID. You trigger the export of these photons. You send them out. Yeah, and this is actually where maybe we still need quantum routing, because in the access networks, I see this as an access network. The core network is only doing teleportation later, so maybe I should have said this before, So it's entanglement distribution, it's teleportation, and the quantum states are being conveyed over the network. In the access networks, we obviously need something like routing, because we might have more than one user of your quantum states, yeah, and this has to be managed. There is teleportation as an example for quantum state in. Yeah? So you're expecting, let's say, an application sending you a quantum state, and you have the protocol layers to do the job, accept the quantum state, offer it in a quantum storage, teleport it over, and do the processing on the other side, and get the quantum state out again. And on the network picture, I mean, this is how it looks like. Yeah, the quantum internet will be very classical. Yeah, it's only teleportation. Yeah, and you see on the user side, no quantum. Yeah, when you get a quantum state in, maybe you need some routing. I don't know. Yeah, when you have it pumped into your first quantum storage of the provider, it's been teleported away. Yeah, and you don't care. It's only classical communication. That's good news, I would say. In that respect. Entanglement out is a use case where you think that the user might control his own entangled states, right? I mean, he doesn't want to rely on the provider, send his photons there to do some processing, but he wants to do it himself. Yeah, you ask the provider for getting entangled states on both sides of the platform and store them themselves and have them under your own control. And there's also a resource use case that I see. Yeah, you ask the provider for quantum resources for whatever reasons. Yeah, you don't want to use this teleportation service. You want to maybe for extra security. I don't know why this might be used, but you're asking for quantum channel that you might use for your own purposes. So that's the architecture and the use cases in the application side. Last but not least, I mean, there's a control plane and time synchronization bit of the story. Yeah. Talked about the time synchronization before. I see it this way. The master is always an atomic clock. So at Deutsche Telekom, we are lucky because we're operating one of the 4 UTC atomic cesium clocks. Yeah, that comes from history because DT used to be a state-owned company. Yeah. 20 or 30 years ago, and from that time it's the leftover. Yeah, that we are actually running these cesium clocks for UTC in Germany. They have a position, I think, of 10 femtoseconds, and I'm not wrong. Yeah, and not the best ones, I would say, but that's the time normal that we can get. Yeah, and we have it integrated in our lab meanwhile. Yeah, so happy about that. And then the idea is to use either White Rabbit. To do some time synchronization in a local lab context, yeah, or on a larger network that I show you if I still have time, where you use optical point-to-point links. Yeah, this is this OTT, optical time transfer technology that brings you even below 1 picosecond time resolution. But what you want to have is actually the time binning. Yeah, that's essential for this whole concept. Maybe I end up with something funny, yeah, because everybody test beds are always interesting to show. That's ours, yeah. So we have a Germany-wide quantum communication infrastructure that we're currently setting up, yeah. So the lower ring, so this is Germany, yeah. So the lower ring, this one here, you see my pointer, that's done within except for one splice. Yeah, that's a 2,000-kilometer quantum communication line. Yeah, that is now in principle made available for basic research in Germany. Yeah, it consists of 3 lines. One is the quantum channel, which is a dark fiber, just we heard in the first talk. There are 2 more fibers for time and frequency synchronization, hopefully with optical links. That's actually going to be the most important or the most expensive part of the network, which we cannot fund out of our own, but it would be very worthwhile to have. And there's a classical fiber, yeah, or actually 2 classical fibers, yeah, that care for all the shifting and classical communication channels. That's the Berlin part of the testbed, yeah. So there are several hundred kilometers that we actually own and can govern, just dark fiber, yeah. We have now the atomic clock connection, a White Rabbit time synchronization network. And yeah, we're eager to actually test new technology, and that's why we're here, why we're working with the universities. HUB is one of the quantum storage providers, yeah, that are pretty advanced, and I really hope, yeah, to get hands on this technology to somehow probe the ideas, understand the capabilities, and probe the ideas that we have. Yeah. And the right picture gives you some glimpse of how this could be integrated. So the big network, the large one, is actually running through the Deutsche Telekom sites across Germany. And it's somehow the fiber appears, yeah, and then it can be redistributed. And the idea is that we integrate university labs via loops, just like the one you showed, I think, in Stuttgart. Yeah, that's one of these integrations that has been already done. So universities can use this more short loop, yeah, to the first experiments, yeah, maybe with current technology. And when there's, let's say, more mature technology available, you can use you can jump onto the larger ring. And this is then the idea is always. When it works there, it will work anywhere, because that's telco network, that's production network that we make available there. Thank you.